Hello everyone, I'm Liheng Zhang from the University of Central Florida. I'm glad to present our work WCP Worst-Case Perturbations for Semi-Supervised Deep Learning. This work was done during my internship in Future Way Technologies. Here we outline this presentation. We formalize previous semi-supervised learning methods as sample-based robustness and propose the worst-case perturbation to introduce model-based robustness. Two types of perturbations on model weights and architectures will be presented following with experimental results and conclusion. And we will show the model-based robustness and the sample-based robustness form an opposite but complementary relationship. Previous semi-supervised learning methods in literature usually assume the predictions of a robust model keep invariance with perturbations on input examples, such as data augmentation, random or adversarial noises on data. They penalize the difference between model outputs with and without perturbations, so as to explore the unlabeled data. They build our sample-based robustness. In contrast, we propose to put worse adversarial perturbations on the model instead of on the input samples. The worst-case perturbation regulator is defined as the maximum distance between the model outputs with and without perturbations. Penalizing this regulator, the model is least likely to be affected by model perturbations, so as to produce stable predictions on both labeled and unlabeled examples. It builds the model-based robustness complementing the sample-based robustness in previous methods. We will discuss two types of perturbations, the additive perturbations on model weights and the DropConnect perturbations on model architectures. For the perturbations on model weights, the perturbation function g is to add noise delta on the weight theta with constraints on its norm. Once we get the optimal noise delta star that maximizes the distance between the outputs of the two branches, we replace the g in the previous formulation with the theta plus delta star to calculate the value of the WCP. Here we show how to derive the delta star. We assume the distance function L achieves its minimum with equal inputs, and it is at least twice differentiable. Taking the Taylor expansion, the additive WCP approximately equals to the quadratic term in the Taylor series. Then the optimal delta star has a closed form solution, which is proportional to the singular vector u theta corresponds to the largest singular value of the Hessian matrix S theta. It can be efficiently computed by the power iteration. Besides, we show the connection of WCP with the max margin principle with a sigmoid example. Consider a sigmoid unit with 2D inputs to make a design boundary on the 4 data points. The WCP curve gets its minima with design boundary x1 equals 0, which is constant with the optimal boundary of the max margin rule. We also observe two local minima of a WCP at x2 equals 0, which is a locally max margin. For perturbations on model architecture, we use a mask alpha to drop model connections with constraints on the DropConnect ratio. Similarly, once we get the optimal mask alpha star that maximizes the distance function, we use it in the formulation to compute WCP. Similarly, we take the Taylor expansion to approximate the WCP. We can get alpha star through solving the constraint binary quadratic programming problem by spectral methods. Details of the derivation are in the paper. Finally, we integrate both perturbations on model weights and model architecture. The semi-supervised objective is a combination of the cross-entropy of labeled data and the WCP regulator on both labeled and unlabeled data. Here we show the experimental results on CIFAR10 dataset. The error rate is reported over 10 runs with the same 13-layer architecture. The WCP outperforms the state-of-the-art method regardless of the number of labeled data. Here is the result on the SVH dataset. Again, the WCP gets the best performances. We performed the ablation study to show contributions of different model components in the CIFAR10 dataset. With more components, the error rate keeps dropping, and we find that putting DropConnect on the second layer of each convolutional block in the 13-layer networks yields the best performance, and the best DropConnect ratio is 0.2. To conclude, we propose our WCP regulator to introduce model-based robustness, which complements the sample-based robustness in previous methods. Two forms of WCP are presented. Experiments show the WCP outperforms many state-of-the-art methods. Thanks for watching. The code is released at GitHub.